I really think this section is fun. Um, at least it's interesting, if nothing else. If you remember on Monday, we talked a little bit about this, and this is the section called choosing a best fit model. So this is modeling data, and I think it's super interesting because it's something that we can use in science class. We can use actually in the real world. If you get data, you can try to model it and use it to predict what's going to happen next. And so what I want to do is I want to talk about this example here. I know you don't have this paper, but let's say that we had someone, oops, sorry, I was trying to do things. All right, make that a little smaller, make that a little smaller. I want to see if anybody pops on the chat too. And where is our thing? Hangouts. There it is. Okay, still just the two of you. Okay, so that and that. Okay, good. I can still see everything. Okay, so let's say that we were looking at your car, and we tried to find out what the fuel efficiency was if you were going at certain speeds. So we looked at the fuel efficiency for your car if you're going 15 miles an hour, 20, 25, and all the way up to 65 miles per hour. Okay, so we looked at the fuel efficiency, and here is the data that we got. And so what we want to do, if we get some data, a lot of times we want to be able to model that data. And so today, for our last lesson, I want to show you how do we model data and how do we try to predict based off of that data other values. All right, so I want to show you how you model data in Desmos. So this is, like I said, a good skill to have. You can also do this on your TI calculator if you would like. Okay. What you're basically going to do is you need to make a table of your data. Okay, so to do that in Desmos, you're going to go in here and you're going to click this and you're going to add a table. All right, so what the table does is that's just a collection of your X and Y points. So what we're going to do is we're going to put our data in as a bunch of points. So when X is 15 miles per hour, your miles per gallon is 22.3. Okay, so this is just a table that I'm going to enter a bunch of data in. So you got 20, 25, 30, 35, 40. You can see it populates it. It kind of does most pretty smart. It figures out what the pattern is for your X's. And then let me make this a little bigger so hopefully we can see it a little more. There we go. That's better. So then I can put my miles per gallon in there. 25.5, 27.5. So this is like data entry, right? We're putting our data into this graph, into the Desmos. Okay. So what I've done is I took the data from my problem and I entered it into Desmos into a table. Okay, so now most of my work is going to be in Desmos. So if I go, now that I have my data entry, I will look and see that my X values go between 15 and 65, and my Y values are basically in the 20s and 30s. So when I enter this data in the table, it actually graphs on Desmos, but you can't see it because none of my values lie in this part of the plane. But if I start to scroll out, you will see, voila, here is my data for X represents the number of miles per hour that I'm traveling, and Y represents the miles per gallon. Okay, so this is your data over here, miles per gallon, miles per hour. And so there's your fuel efficiency chart. Okay, and we talked about this in class on Monday. There's like kind of a sweet spot. I think they usually say around 50 miles per hour is kind of the sweet spot, which does look, it's right about here. That's when you get the best miles per gallon for your car. If you're doing like a lot of slow traveling, you don't get as good of gas mileage. And if you actually go fast, you don't get, your gas mileage is not as good. Okay. So just looking at this graph, right? Your X is your miles per hour, your Y is your miles per gallon. What do you think best models this? Do you think this looks like a linear model? What do you think? Does it look like a line? All right. I'm just going to go ahead and tell you guys it's not a line, right? It's not a line. This looks more like a quadratic, like it's got a nice curve to it, right? Looks like something that's quadratic. So what I want to show you, I know your brains are all on like vacation mode, but I want to show you how do you actually make a model of this data, okay? So in Desmos, what you can do is you can ask Desmos to model your data. So notice that your X values are X sub 1 and your Y values are Y sub 1. So we want to figure out an equation that models this. So what you can do is you can make a little model. And I'm going to type this in and then I'll explain it. So you do X sub. So yeah, let me type it in and then I'll explain it. Oops, sorry. Okay, so I typed in a bunch of values, okay, and what I typed in here, this looks like a, oh, hey, Anton, how are you? So what we're doing, Anton, is I had this problem that was speed versus efficiency. So this is a bunch of data that shows the X values are your miles per hour and your Y values are your miles per gallon that you get for your car. Okay. And so what I did is I took that data and I put it in Desmos as a table. So I added it as a table, and the green points are my data points that I had. That's just the data that I collected. Okay, so that's my data that I collected. Then I just typed this in, and I was telling Aaliyah and Kirsten, I'm going to explain what this means. So this equation is an equation for a quadratic, right? It's ax squared plus bx plus c. That's a quadratic equation. And what I've asked Desmos to do is I've said, can you approximate a quadratic equation? And I want you to use my x sub 1 values, which are these values from this chart. This is x sub 1. And figure out, how do I make x sub 1 equal to y sub 1 in the best way possible? So I do that using this, and then instead of an equal sign, the way that Desmos knows to model something is by this tilde sign. It says basically approximate it, okay? So what Desmos does is they take that table of data and they have something called regression software, and behind the scenes, they figure out what quadratic equation best fits this data. Okay, so you can see down here this A, B, C. What that means is this means that this value right here, negative 0.007930007, that goes right here for this A. And 0.726 whatever, that goes for B, and then 13.75 goes for C. So if I wanted to write this as a model, I would say y equals negative 0.0079307 x squared plus, and then I take my B value, 0.7296951 x plus 13.7562. So can you see how I took what Desmos calculated for me, and then I can just write it as an equation, and it's the same equation. So now this quadratic equation that I just wrote out here, I could say models my data, right? It models my data. And how do we know if it models the data well? Well, there's something called the correlation coefficient, and that's this value called your R value, okay? And the closer that R gets to 1, the better your data is modeled. So this is pretty good. It's got an R value of 9.619. So it models my data pretty well. Does that sort of make sense what I just did? I took my data, I asked Desmos to make a model for my data, and I picked quadratic because it looks like a quadratic, and so then I was able to come up with an equation to model my data. Okay? You guys following? Your brains are all like mushy, you can't think? Okay, cool. All right, so I just want to show you, let me turn this one off. That's the one we did. I'll take this that we just did, the model. What if we had tried to model this as a line? So the equation of a line is y equals mx plus b, right? Y equals mx plus b. I'm just going to do to the 1 power. There we go. All right. So if I tried to model this as a line, is the line a very good model for this data? Line is a terrible model for this data, right? And we know that because look at our R value and our R squared value. This is our coefficient. It's a 0.625. Like it doesn't really model our data that well. So sometimes you have to look at your data and decide what is our best model for my data, right? So this one, line is not good. We should stick with quadratic. Okay. So let's stick with our quadratic. The question is, based off of this, could you predict what my miles per gallon, I would get at 70 miles per hour. So my highest data point, you remember, is 65 miles per gallon. Could you predict what my miles per gallon is at 70? Yeah, we would just follow our curve, right? And at 70 miles per gallon, we would estimate that you would get 25.785 miles per gallon, right? You could also predict within, like, oh, at 57 miles per hour, what's my miles per gallon? You can do that too. Do you think that you can accurately predict, don't ever do this, but if you were traveling at 120 miles per hour, if your car could get that fast, do you think you would really get a negative miles per gallon? No, right? So there's some limitations. You can't extrapolate that far out. You can't go from your highest data point being 65 miles per hour and try to extrapolate out to 125 miles per hour, but you could extrapolate out to 70 and kind of see what you think the trend would be going forward, right? I'd say so. All right, so what I'd like to do, I want to do one more problem, and I want to pick one from your homework, so you can hear me unzipping my bag to get out our book. So the homework is basically 4 problems. So there's 10, 11, 13, and 14. Okay. I don't know. Anyone have any that they really want to do? Let's do number 10. Okay. So this is on page 779, number 10, and it's, I'll read it to you. I don't have it up on the screen, but that way it's one less homework problem that you have to do if you came on the call today. How's that sound? Okay. It says, this is a word problem from economics. The gross domestic product, the GDP, is the total value of goods and services produced by a country in any given year. So US either has the highest GDP or one of the highest. I don't know if it's China or US has a huge GDP. So the GDP is all the goods and services produced by a country in a year. There is a table that shows the GDP, which is represented by Y, in billions of dollars of the United States for selected years from 1930 to 2000. In this table, X represents the number of years since 1930. Use a graphing calculator to find a model for the data. Okay, so we're going to model this data and try to figure out which one's best. All right, so I'm actually going to use my existing table, but I'm going to delete everything out. Maybe I'll just start a new table. Is there a quick way to delete? A little too excited there. All right, there we go. All right, I'm going to leave these guys on here, and you'll see why in a minute, so I don't have to retype things. Okay, so let's start a new table. So we would go in here, we would start a table. I want this actually to be X sub 1 though, and Y sub 1. Okay, so in 1930, we're going to call that year 0. Okay, in 1930, the GDP was $91.3 billion. Okay. In 1940, so it's 10 years after 1930, so we're going to type in 10. In 1940, the GDP is 101.3. Okay, and then in 1950, so we're just going to go ahead and put all these values in. 0, 10, sorry, 20, 30, 40, 50, 60, 70. Okay, so X equals 70 would represent 70 years after 1930. So that's the year 2000. All right. And then over here represents your billions of dollars. So I'm going to go ahead and type these in. I'm getting these values from your book. There's a table in your book. Okay, so I'm getting these values from your book. What do you notice as I'm typing in this number? Is the GDP going up every year or every 10 years? I'd say so, right? The GDP looks like it's going up. So the first thing is we got to be able to look at these data points on the graph. Actually, let me turn off these things. Let's look at this graph. Trying to turn it off. There we go. So this has the domain is from 0 to 70. So you can actually go into your graphing calculator and set the domain. You can do this on on TI too. So I want my x's to go from, let's say, 0 to 80. Okay. My GDP goes from basically 0 to, I'm going to go all the way up to 10,000. See how I put that in there? Because I've based it off my range. And then I can kind of play with it from there. All right. So here is my graph of my data, how the GDP for the US is growing over time. Okay. So I left up my equations that I've written on here because I knew that I didn't want to have to retype them again. Again, to get Desmos to approximate, the key is that you have to put in x sub 1 and y sub 1 to make it draw the data from your chart. And then you put in this little tilde guy that tells it to approximate it. So if I wanted it to approximate a line, do you think a line, Desmos calculated my best fit line, do you think this line best appropriates my, best fits my data? Nope, bad, right? Not work at all. So let's try quadratic. Let's see how quadratic looks. Quadratic's not bad, right? I'm kind of missing this at the bottom though. There are other ones that we have though. We have 5 actual different models that we can choose from, at least in this book, and they're all on page 775. So that's a linear and the quadratic, but really what this looks like to me is it really looks like an exponential function. So let's put that in as a possible model. So instead of y equals mx plus b, let's do y equals a times b to the x1 power. So it's a little difficult to type in these, but once you type them in, if you just keep changing the equation, or if you leave the equation on there, it's not too difficult to do. Okay, so what I typed in is a general formula for an exponential equation, and look at that beautiful graph there. Does that look like it models it well? I think so. That looks like a really nice model of my data, right? It kind of gets the initial and then the growth. So if I wanted to find a model for my data, which is what number 10 says, I would pick this model. I would say an exponential model fits best. And if I had to write down what this equation is y equals, and then here's my a. So it's 111.429 times 1.06639 to the x power. So that's how I take this a and b and I put it into my model, and then it becomes an equation. So this is what I would write down as my best model for my data. Okay, so based off of this, now that I have a model, and you can see the blue and the green are right on top of each other because they're the same equation, what would you expect the GDP to be in? So we have, let's see, It starts in 1930 and 70 years out is 2000. So what would you expect the GDP to be in 2010? That would be 80 years past 1930, right? So at 80, let's see, at 80 years in 2010, if I can get there, there we go. The GDP, that would be in the trillions, right? Because this is billions. 19 trillion and 67 billion if the trend continued. All right, I'm going to do a quick Google search and tell you. US GDP in 2010. All right, so in 2010, the GDP was 14,994,000,000. So basically 15 billion. And our graph predicted that it would be 18 billion versus 15 billion. So I guess it slowed a little bit. I kind of didn't keep going exponentially, right? However, if I wanted to predict inside of here, what was the GDP in 65 plus 30, 1995, right? In 1995, this would probably be a lot more accurate. So GDP in 1995. See how well I can type and work at the same time. GDP 1995. I can't find it that easily. But anyway, if you look at data inside, it's probably going to be a little better than if you look at data outside. All right. Do you guys think you can do it? Cool. So basically you have 3 problems to do. Let me know if you guys have any questions. I will send out a little mini quiz by the end of today. And it'll just basically have a little problem from each section. It won't be weighted the same as a whole test, but just kind of a check for this section that we did. All right, guys, thanks for coming today. I hope you have a good rest of your day. Aaliyah, you're officially done with high school math. Well, once you finish your homework, right? And we'll talk to you later. Oh, she's gone. All right, bye. Thanks, Anton. Bye, Kirsten.